All right, let's take a look at this static equilibrium problem. So we're going to try out those steps that we just learned. We got to draw a free body diagram. We really want to make sure it's big so that we can fit all of our information on it. We're going to remember to draw the weight at the center of our object, and we want to make sure we label all those intermediary distances. We're going to choose our axis of rotation. I'm going to go through some of the explanation of how I make that choice. We'll identify the torque direction, so I know if it's a positive or negative. We'll figure out some ways that we can remember how to figure that out. And then we'll generate our equations and solve. So let's go ahead and take a look at this first one. It says a 7-meter long board with a mass of 25 kilograms is supported by 2 supports. The left support is 1 meter from the left end, and the right support is 3 meters from the right end. What is the upward force supplied by both supports? Okay, so the first thing I need to do is draw a free body diagram. So we have a weight, so I'm going to make that weight act at the center, mg. And so they told me that m was 25, so I have 25 times 9.8 here for my mg. And then I have these 2 supporting forces. And so I see that I have F1, we'll call it, and F2 right at those 2 little supports that are underneath the beam there. And I have my free body diagram set. Now there's a couple extra things we have to do now because we're doing torque, and torque is a force times a distance from the axis of rotation. So I'm going to need distances. So it's very important when I draw these free body diagrams that I locate where that force actually is. So for instance, they said that this first force was 1 meter from this end. The second support was 3 meters from this end. The whole thing is 7 meters. Now when I draw these, I want to just draw all the increments that make up the whole. You want to try to shy away from like doing them all from one end or something like that. It just makes our calculation of how far away the force is from our axis of rotation a little easier. So mg is at the center of our 7-meter thing, so that means it's 3.5 meters from either end, making this distance 2.5 meters and making this little distance in here 0.5 meters. And just as a quick check, all of these should add up to 7. They do, we're good to go. All right, so we have done the first 2 steps here. We're on to choose an axis of rotation. Now when I choose an axis of rotation, I try to eliminate some unknowns. So let's just see why I do that. So I'm going to skip down and I'm going to do the sum of the forces in the x and the sum of the forces in the y. Well, if I look at my problem, there are no forces in my x direction. So when I say sum of the forces in the x direction equals 0, there aren't any. However, when I generate my sum of the forces in the y direction, I have F1 plus F2 minus mg equals 0. Now the problem here is I have 2 unknowns in this equation. So ideally, if I want to find F1, I need to know F2. Or if I want to find F2, I need to know F1. So I need 2 equations, 2 unknowns. Now it's easier to solve an equation if there's only one unknown in it. So what I want to do when I choose my axis of rotation is I want to choose it so it eliminates an unknown. So let's think about what torque is. So torque is force perpendicular times that distance, that lever arm. So I'm going to go ahead and say, well, how much torque would F1 produce if this was my axis of rotation? And the answer is 0, because how far is F1 from my axis of rotation? 0, so it produces 0 torque. So now when I generate my torque equation, F1 will not be in my torque equation because it's been multiplied by 0. So this is the trick we're going to use to eliminate an unknown. All right, so I'm going to choose my axis of rotation there. I also like to choose my axis of rotation at a point on the left. And you're going to see why when we do our next step, when we identify the torque directions. All right, there's 3 ways to do this available to us. One of them is you can just kind of use the right hand rule, if you're familiar with it, where you point from your axis of rotation to the force. You use your F finger in the direction of the force. So for instance, mg is pointing down, and then my thumb points into the board, which is my negative direction. The other way, and probably used more often, is you get a meter stick. Let me grab one here quick. and you hold it on the board and you say, okay, what if I am that mg and I push and I only hold it at the axis rotation, and I push like I'm mg, and I see which way does that rotate. So when I push like I'm mg, this rotates clockwise, and clockwise is my negative direction, so this will be a negative torque. All right, and then the last option for us is, and this is more of a wordplay one, if the force is to the right of the axis rotation, the direction of the force is right for the direction of the torque. So if the forces are to the right of my axis rotation, which both of these are, the direction of the force, so negative, is the same as the direction of the torque. So this will have a negative torque, just like we had clockwise and using the right-hand rule. This one is pointing up, so it will have a positive torque. And you can just conclude then that if the force is to the left of my axis rotation, we just have to flip the direction of the force to get the direction of the torque. Or use your ruler on there and decide is it positive or negative. All right, now that I have those done, I can generate my equation. So here we go. The sum of the torques equals 0 because it is not angularly accelerating, much the same as it was not linearly accelerating. And I'm going to write the first one out just to show it. So I have F1 times 0, and then plus F2 times, all right, now I got to figure out how far is F2 away from F1. Well, it is 3 meters, okay. And then minus, because it's a negative torque, mg times how far away it is, 2.5 meters. All equals 0. Now when we do this, because that axis rotation was at F1, it's gone. It's not in our problem. 0 times F1 is 0. All right, so now I just need to go ahead and solve for F2. So F2 is going to equal mg times 2.5 divided by 3. Common mistake here. When we are doing these problems, you get used to writing that force equation. Then when you go to write that torque equation, you cancel out the F1, but you forget to put those R values, and that doesn't work. So by all means, make sure that you have F times R every single time there, okay? So plug in your numbers. The mass was 25, the acceleration 9.8, and you should get 204.2 newtons. Okay. Now, we want to go ahead and find F1. Well, the easy way to do this would be to go ahead, take F2, plug it in here, and solve for F1. But we're going to practice something here. So what I want you to do is I want you to go ahead and try and choose an axis of rotation such that you would find F1. So what we're going to do is move our axis of rotation to here and generate a torque equation and see if you can solve for F1. Give it a try. Pause the video. I'll show it in a second. All right, so you've chosen your axis of rotation here. So what we need to do is we need to do a couple new things. We need to make sure we identify the direction of the torque. So both of these are to the left. That means that their direction of torque is opposite their direction of force. So this is pointing down, so it will have a positive torque. This is pointing up, so it'll have a negative torque. If you want to use kind of that other idea, if I push down on mg, it's going to cause my pencil or whatever to rotate counterclockwise. Pressing up like F1, it rotates clockwise. So that's how we get the positive and the negative. Right hand rule, same kind of idea. I point from the axis rotation to mg, pointing, and my torque is out of the board, which is my positive direction. All right, so let's generate that equation then. So for that torque equation, you should have your F2 times 0 plus mg times 0.5 minus F1 times 3 equals 0. You should be able to then solve for F1. F1 should come out to be 40.8 newtons. And again, we just did it this way to practice choosing that axis of rotation and generating that torque equation. In the future, you can just put it into the y direction.